In this lecture, we shall study some physical observables and the corresponding linear Hermitian operators. The first one is the position. This is a physical observable, and yes, it is x or r, and the corresponding linear Hermitian operator is x hat or r hat, and the operation by the operators is just like multiply by x or r. For example, if we have the operator, position operator, it operates on a state function psi, then it will be just it will be multiplied by x. Okay, similarly, if you consider linear momentum, it is denoted by small p, and the operator is small p hat, and operation will be, it is denoted by this, and the operation, if the linear momentum acts on a state function psi, then it will be just minus I h car del psi, where h car is h by twice pi. Okay, and we know the del operator is the vector del operator. Okay, the third physical observable we consider is angular momentum. And it is denoted by small l, and the corresponding operator symbol will be small l hat, and the components of L, there will be three components, and the x component of the angular momentum should be this. Similarly, the y component of angular momentum will be this. And the z component of the angular momentum there is a way you can remember this. When you consider x component, then you see minus I squared will be multiplied multiplication factor, and if you consider cyclic order, it is x, this is y, and this is z in the anti-clockwise direction. So if you take the x component of angular momentum, then here y and the derivative with respect to z, and then minus n, and these will be exchanged, so is z here and y here. Similarly, when you take the y component of the angular momentum ly, so here will be next z and the derivative with respect to x and minus, and these will be exchanged, okay, like this. Okay, now the fourth, the physical observable is the kinetic energy. And kinetic energy is denoted by T, and the operator symbol is T hat, and which is actually minus h cut square by 2m del square. Okay, and this is potential energy. Potential energy is denoted by V, and the operator symbol is V hat, and is just multiply by V. Operation is just multiply by V. That means if this operator acts on a state function, and the state function will be multiplied by the potential energy. Okay, now we have the last one is the total energy, total mechanical energy. Is denoted by E, and the operator symbol is H hat, and this is T hat plus V hat, which is equal to minus square by 2m del square and plus V. So if we have a state function psi, and if h operates on that, that means you'll have then put here minus square 2m del square plus V, and here psi. Okay, now we shall consider postulate 3. Postulate 3 of quantum mechanics. It says that the only possible experimental results of a measurement of an observable are the eigenvalues of the operator that corresponds to such observable. Mathematically, when the operator A acts on the state function psi, A will have an eigenvalue small a and the state function psi. This postulate captures the central point of quantum mechanics. The values of dynamical variables can be quantized, although it is still possible to have a continuous of eigenvalues in the case of unbound states. If the system is in an eigenstate of capital A hat with eigenvalue small a, then any measurement of the quantity A, capital A, will yield small a as the eigenvalue. Okay, we will have now the postulates. Postulate 5. I am sorry, postulate 4. The average value of many measurements of an observable say A, capital A, when the system is described by the state function psi is equal to the expectation value we will denote the expectation value by this expectation value A, which is defined as follows. The expectation value f of A equal to, you will have to take the integral over psi star, and the operator corresponding to A is A hat psi, and the volume element divided by the integral over psi star psi dv. If the state function psi is normalized, then we know the normalization condition psi star psi dv. Integral of this is modulus of psi square dv, which is equal to 1. We know the normalization condition because total probability is 1. Then the expected value of A will be just this one. Okay, we have the last postulate, postulate 5 now. The wave function or state function of a system evolves in time according to the following differential equations. I square del psi by del t equal to a psi, where h is the Hamiltonian operator of the system, where h equal to minus square by 2m del square plus v is the Hamiltonian of the system. Hamiltonian or total energy operator of this system. The above equation is known as the time-dependent Schrödinger equation. And this V is the potential energy of the system. And V is a function of position, usually is a function of position. So that's all for the postulates. So we have discussed 5 postulates, and we shall now study 3 theorems. These theorems are the outcomes of the postulates. Okay, the theorem 1. And this theorem says that the eigenvalues of a Hermitian operator are real. Okay, the eigenvalues of Hermitian operator real. We know the eigenvalue equation. We know the definition of Hermitian operator. All we know. Now we are going to prove this theorem. Proof of this theorem. Let us consider a Hermitian operator capital A hat with eigenvalues an, where n equal to 0, 1, 2, dot. When it acts on the state function psi n. Therefore, the eigenvalue equation is a psi n equal to a n psi n. Let us suppose this is equation number 1. Okay, here an is the eigenvalue of the operator a, capital A hat. We have the inner product this is from definition of inner product. If you substitute 1 here, we bring an, this is eigenvalue constant, bring outside, and this is psi n star psi n dv, and this is an, and this is the inner product of psi n with itself. Let us suppose this is equation number 2. We also have reform this inner product where dv is the volume element. Bring this outside n star, and which can be written as this. Let us suppose this is equation number 3. Now we can equate equation number 2 and equation 3 because capital A hat is a Hermitian operator. We know for Hermitian operator, since A hat is a Hermitian operator, we have this. This is from definition of Hermitian operator. Now using 2 and 3, we obtain this, and from this this. Now, since the inner product of a state function with itself cannot be zero, this one cannot be zero, is not equal to zero, because inner product of a state function with itself never be zero. Therefore, this equal to zero, which shows that for an equal to an star. Star asterisk means complex conjugate, you know. This means complex conjugate, which implies that the eigenvalues an are real. Therefore, we have proved that the eigenvalues of a Hermitian operator are real. Okay, the next theorem is theorem 2. Says the different eigenfunctions of a Hermitian operator with unequal eigenvalues are orthogonal to each other. Proof of this theorem: let us consider a Hermitian operator capital A with eigenvalues am and an when it acts on the eigenfunctions psi m and psi n respectively. Therefore, the eigenvalue equations are when A acts on psi m gives you A m psi m, Let us suppose this is 1, and when capital A acts on psi n gives you a n psi n. Where psi m where for m is not equal to n, am is not equal to n. This is given. N is given. The unequal eigenvalues for different eigenfunctions. If m is not equal to n, then psi m and psi n are different eigenfunctions. And in that case, it is given that the eigenvalues are unequal. Am is not equal to n. Then we'll have to show that we will have to show that psi m and psi n are orthogonal. That is, the inner product of psi m and psi n is 0. So if the inner product of two eigenfunctions is 0, that means the eigenfunctions are orthogonal to each other. Okay, now we set the inner product. We have a psi m and here psi n. Okay, first one's asterisk. It's a dv volume element, and if you apply 1, you see this one, equation 1, then am psi m asterisk means complex conjugate, psi n dv. Because eigenvalues are real, and this can be written as inner product of psi m and psi n. This is from definition. Let us suppose this is equation 3. Also we have psi m and a psi n. Now using equation 2, you see a psi n here, this one, a n psi n dv, and this one can be written as this. Let us suppose this is equation 4. Now we will equate equation 3 and 4 because capital A is Hermitian. Since operator A hat is Hermitian, we have this. this is the condition for A being Hermitian, operator A Hermitian. Now using 3 and 4, we obtain but we are given that the eigenvalues are unequal. AM is not equal to AN, therefore we have inner product of psi m and psi n is 0, showing that the eigenfunctions psi m and psi n are orthogonal to each other. If we summarize what we have studied in this lecture, first we have considered few physical observables and their corresponding linear Hermitian operators. And then we stated and proved two theorems. Theorem 1, which was the eigenvalues of Hermitian operators are real. And theorem 2, different eigenfunctions of a Hermitian operator with unequal eigenvalues are orthogonal to each other. And we have proved these two theorems. In the next lecture, we shall state and prove another theorem, and then we shall study the Schrödinger equation elaborately. That means we shall actually derive time-independent Schrödinger equation from the time-dependent Schrödinger equation. Today we stop here.